your links?
Yes.
Okay.
Yes.
Yes.
Okay, great. So let's start today. So as usual, so I'm going to start showing you the Moodle platform, the Moodle page for our course. So I guess that all of you have access to Moodle now. So if you can do that, if you can try to access it and download the syllabus, that'd be great. Okay. But in the meantime, I'm going to share my screen. And I'm sharing it. I think so, right?
Yes,
Yes.
you are.
Thank you. Okay, so as usual, as before, in all my courses, my Moodle page has the same structure. So I try to include some beautiful pictures. In the presentation, after the picture, then I have some information from the syllabus. Okay. So the first lines are from the syllabus, including the course objectives, the course description, independent study, learning outcomes, assessment method, and study literature. So I included 4 links, but the textbook that we are going to use in this class, in this lecture, will be number 4. Okay, so this book, a first course in optimization theory by Cambridge University Press. Okay. So, and over there you can find the link, you can download it, and you can follow the course from the textbook. Okay, and then I have the syllabus, and here I have a link. Some students last year gave me this link. This link is about, it's a dictionary of mathematics to translate terms between Estonian and English. So if you go to that link, I think, oh, it's not. Oh, here. Yeah. So I guess this will help you translate terms, mathematical terms between English and Estonian. So I hope it's useful. Okay. Then I have the first topic, which we're going to start to cover today, which is preliminaries. And the idea is the same as with the other courses. So I'm going to explain it briefly. This is optimization. This is okay. Mathematical modeling. So the presentation is always the same. So at the beginning, I give you introduction. Then for each of the topics that we are going to cover, so there will be some link here in which you can find the lecture video, which I'm going to include every day. And you can also download the lecture whiteboard, which I'm going to produce every single day. Okay. And again, so when there is a new topic, there will be a nice picture and then part of the syllabus corresponding to that topic. So I don't know, I think it's basically very straightforward. I don't know if you have any questions about the structure of the Moodle page. Any questions?
No.
No. Okay, very good. So the first thing I'm going to do today is read with you the syllabus. So I'm going to open it. Okay, I'm downloading it. Let me see, how do I open it? Okay, open. Okay, so this is the syllabus. The course title is Optimization in Economics. And again, we are in the School of Digital Technologies. And the department is Mathematics and Didactics of Mathematics. And this is an important number for the course catalog. And these are standard information. Okay. Again, this is my name. But you can just call me Jorge or George as you wish. That's fine. And this is what I wanted to talk to you about. So what is the meeting days? Only Thursdays? Tuesdays and Thursdays?
Yes.
Okay, so I'm going to change this. Okay, so it's not Fridays. Okay,
No.
last year it was Tuesdays, and 1 week it was Thursdays, the other week was Fridays, then the next week Thursdays, and then Fridays. Okay, so this semester it'll be Tuesdays and Thursdays. Am I correct?
Yes.
Okay, great. Thank you. And it'll be basically during lunchtime for you. Okay, from 12:15 to 13:45 hours. All right, so I'm going to read the course objectives. And this time I think I'm going to let you read also. Okay, so I'm going to start with the course objectives. So the objectives are enable students to obtain a rigorous mathematical background to optimization techniques used in areas such as economics and finance, and enable students to understand the connections between the several aspects of continuous optimization and about the suitability and limitations of optimization methods for different purposes. So basically, this is an introduction to optimization. Last semester, you took operations research, and operations research was a subject in which we didn't cover many proofs. This time, we are going to justify basically everything. So we are going to see proofs, but we're going to see also examples and applications. Okay, so the course description, does anybody want to read it, please? Or I can read it, that's fine. The structure of the course includes strict abstract construction of linear spaces, metric spaces, calculus of functions of several variables, a general problem of optimization of function of several variables without restrictions and with restrictions, both the identities and inequalities, finite and infinite horizon discrete dynamic optimization. The course materials should teach students to understand and prove the basic formulas of optimization theory and to investigate the economic problems of comparative statics and dynamic optimization within the framework of developed tools of mathematical models. Okay, so the course is a little bit ambitious, but basically we're going to cover everything related to optimization with and without restrictions. Sometimes the restrictions are going to be identities. Some other times they're going to be inequalities. Okay, and we are going to see theorems that you probably know, Lagrange's theorem, and others that maybe you don't know, for instance, the Kant-Tucker conditions for inequalities. Okay, for independent study, you will be in charge of processing lecture material and the literature, completing homework assignments, process-based learning assumes participating in auditorium classes. Okay, so that's standard. And about the learning outcomes, at the end of the course, the student will be able to use theoretical notions and concepts of relevant parts from real analysis with emphasis on higher dimensions, use the Weierstrass theorem in optimization problems, use both the first order and second order conditions in unconstrained optimization problems, be able to use the Lagrange multipliers approach and analyze the solutions, formulate an optimization problem under inequality constraints, use the Kant-Tucker approach for optimization problems, and use theoretical notions and concepts of concave analysis under solution of different optimization problems. Okay, so there are various results that you probably know. So already you know the Weierstrass theorem and the technique of Lagrange's multipliers. And as I said before, this is also an important result that we are going to cover, the Kant-Tucker theorem. Okay, so about the assessment method. So there will be 4 homework assignments during the course. The homework problems will be announced in class and they must be turned in for grading. The due dates will be also announced. The homework grade will represent 60% of the final grade, and the remaining 40% will be calculated by means of a take-home final exam, which will be based on homework problems assigned in class. Okay, and is this crystal clear, guys?
Yes.
Is okay. So
Yes.
just okay, great, thank you. So just to emphasize it, so we are going to have 4 homework assignments. So in all, there are going to be 40%. So basically, each of them is going to be 10% of your final grade. I'm sorry, that'll be 60%. So homeworks will be 60% of the final grade, and the final take-home exam will be 40%. Okay, so about the date of the homework problems, so I'm going to announce them, and also we are going to talk about the final exam date in time. Okay, so when time approaches. Okay, so about the study literature. So I'm proposing all of these books, so which you can download freely. But as I said before, the textbook for this course will be this book, which you can download already. Please let me know if you can't. In that case, I'm going to give you a copy of the textbook. I was planning to place it in Moodle, in the Moodle platform, but I think that we would get in trouble if I do that because we are not downloading them for free. So I encourage you to try to download them on your own, please. Okay, and this is the syllabus, okay, the contents, the topics that we're going to cover. So we're going to cover various topics, and I'm proposing the goals for each week. Okay, so this is the preliminary section, and this is the objective. I'm going to read it. At the end of this topic, the students will remember some important results on the differentiability of real valued functions. Okay, and you're going to tell me most of these results are results that we already know. And you're right, but since probably you've never taken mathematics in English, so I'm going to cover these topics just to make sure that we use the same notation, the same notions, the same definitions, okay? So that's the idea. So this is going to be like a summary for week 1. Yeah, and any questions, any comment?
Yes. I actually tried to download the fourth book, but I couldn't. So I'm
You
just letting you know.
Oh, thank you.
That, so
Let me see.
maybe.
Let me see. What I do is I copy the link and I paste it in Firefox. Did you reach this page?
Yes. And
Okay.
I also download, but okay. For me, it just went to a blocked page and.
Oh, you know what? I think that it's blocked within your university, within Tallinn University. So if
Okay.
you go to, yeah.
I will try then at home. Maybe
Okay.
I can do it then.
Yeah, it's taking some time, you see, over here, but it's downloading. Yeah.
Okay. I will try later then. Thanks.
Okay. Yeah, great. And alternatively, I can try to send it to you through email, but I don't remember. Maybe it's a little bit too big. let me see, it's 13 megabytes. It's not so big. So if you have problems, let me know. Okay. So is any of you at home right now?
Yes.
Yes, and are you able to download it?
I'll try.
Okay, please. Mm-hmm. Okay, in the meantime, I'm going to continue with the contents. So as I said before, I'm going to cover these topics mainly to speak the same language, same mathematical language. So I'm going to introduce the definitions of supremum and infimum, liminf and limsup, continuity and differentiability, partial derivatives and differentiability, higher order derivatives, the mean and the intermediate value theorems, the inverse and implicit function theorems. Okay, in my case, it just downloaded the book. Sorry. Okay, and that'll be for week 1. For week number 2, we're going to talk about some product transpose of matrices, some important classes of matrices, the rank of a matrix, the determinant, the inverse, calculating the determinant, so basically properties of determinants, quadratic forms and definiteness, and identifying definiteness and semi-definiteness. These conditions are going to be very important. Those are going to be conditions that will appear as necessary or sufficient conditions in order to guarantee the existence of a maximum or the minimum of a function. Okay, so this is the preliminary section. Then we have topic number 2. So this will be optimization in Rn. So we're going to talk about how to optimize functions that go from Rn into R. And the objective is, at the end of this topic, the students will remember some results on the optimization of real valued functions and will apply them to the solution of some problems in economics. Okay, so for week number 3, we are going to cover optimization problems in Rn, optimization problems in parametric form, some examples in economics, and the objectives of optimization theory. This is the roadmap is what we are going to cover in the next sections, okay, for topic number 3, 4, and so on. Okay. And topic number 3 is existence of solutions. So it says we are going to cover it in 3 weeks. That's not true. So it'll be 1 week. Okay. The objective is, at the end of this topic, the students will be able to use the Weierstrass theorem to establish the existence of solutions of some optimization problems. And in week number 4, we are going to cover the Weierstrass theorem. We're going to prove it. So we are going to see some applications. Okay, and as I said before, so we are going to establish a proof for this theorem. Okay, the next topic is unconstrained optima. So what is this essentially? So we are going to optimize functions without constraints. So functions that go from Rn into R. And the objective is, at the end of this topic, the students will be able to use the first and second order conditions in optimization problems without constraints. So for week number 5, we're going to cover unconstrained optima, first order conditions, second order conditions, using the first and second order conditions. And we are going to provide proofs for the first order conditions and second order conditions. Okay. So for topic number 5, we're going to talk about equality constraints in the theorem of Lagrange. So in this case, so we are going to optimize a function. And the conditions are going to be identities. Okay, and the objective is at the end of this topic, the students will apply Lagrange's theorem on constraint optimization problems when the constraints are identities. So week number 6, we are going to see constraint optimization problems, then equality constraints and the theorem of Lagrange, second order conditions, and using the theorem of Lagrange. Week number 7, so we're going to cover 2 examples from economics, a proof of the theorem of Lagrange, and a proof of the second order conditions. Okay, so for this, all of these proofs, basically we're going to use calculus, vector calculus, and sometimes metric spaces, but that's it. Okay. Topic number 6, inequality constraints and the Kant-Tucker theorem. So the objective is at the end of this topic, the students will be able to use the Kant-Tucker theorem in the solution of constraint optimization problems when the constraints are inequalities. Okay, so Kant-Tucker R4 is a theorem for optimization problems when the constraints are inequalities. So that's something important to remember. Week number 8. So we cover the theorem of Kant-Tucker and how to use the theorem of Kant-Tucker for optimization problems. Week number 9, we are going to cover illustrations from economics, some problems from economics. The general case when you have mixed constraints, so that is equality, identities, and inequalities. And we are going to close this section with a proof of the theorem of Kant-Tucker. Topic number 8 is inequality constraints and the Kant-Tucker theorem again, but using some other tools, some convexity tools. At the end of this topic, the students will be able to use the Kant-Tucker theorem. Okay, maybe I just copied it. So here we're going to cover, I'm sorry, this is wrong. So my fault. So what we're going to do is we're going to cover optimization problems using convexity conditions. So we're going to define convexity and some implications of convexity in week number 10. And in week number 11, we're going to cover convexity in optimization, using convexity in optimization. Number 12, week number 12. So we're going to establish a proof of the first derivative characterization of convexity, a proof of the second derivative characterization of convexity, and finally a proof of the Kant-Tucker theorem under convexity. And the last topic is quasi-convexity and optimization. So basically we're going to cover the same topics, but now relaxing the condition, not convexity, but quasi-convexity. The objective is at the end of this topic, the students will be able to solve optimization problems using the quasi-convexity condition. Week number 13, so quasi-concave and quasi-convex functions. Quasi-convexity is as a generalization of convexity, implications of quasi-convexity, quasi-convexity in optimization, and in the last week, using quasi-convexity in optimization problems, a proof of the first derivative characterization of quasi-convexity, a proof of the second derivative characterization of quasi-convexity, and finally a proof of the Kant-Tucker theorem under quasi-convexity. So those are all the topics that we're going to cover in this semester. Do you have any comments, guys? Any questions?
No.
No, okay. Okay, maybe it's too early to talk about this, but this semester we are going to see more proofs. We are going to establish examples and counter examples also. So this course will be a little bit more mathematical. but of course not as mathematical as, for instance, real analysis that you're taking right now, I think. Okay, my question to you who are at home, could you download the textbook?
Yeah, with no problem.
With no problem, right? Okay, great. So I guess that's only the restriction in your university. Okay, so once you go at home, please try to download it. Okay, any questions? Any comments before we start? Comments, questions? No? Okay, now question to you. This time suits you well. It's a good time for you to take the class, right?
Yes.
Okay, great. So I want to ask you to again make a WhatsApp group for this class. Probably Hilary and Eva. Could you help me with that?
Yes, I already made a note to myself that I need to make 2 WhatsApp groups. So yes, I'm on it.
Okay, thank you very much. And right now I don't have my cell phone with me. I don't know where I left it, so that's why I told you to do it. Probably you already did it for um, uh, mathematical modeling, but if not, well, maybe for the weekend.
I'll try to do both of them today, hopefully, but for the next lesson, definitely. So
Okay.
they're gonna be there.
Great, thank you very much. So yeah, if you can do it during the weekend, that'll be fine. And as I told you, this is just in case of emergency. In case, for instance, the internet fails. So it never happened before. No, it only happened once, right? Last semester. So, okay. So just in case it happens. Okay, and also in case that you want to ask me questions, you will also have my contact. You can send me in messages. That's fine. So that's the reason to do that. All right. So any questions? No questions. No. I think that this semester I recognize Agnes. Were you with us last semester?
Of course.
Yes, right. So I knew that. You see. Okay. And Ellis Sodla, were you with us last semester?
Yes, I used to watch your videos.
Okay.
From Moodle.
Okay. Okay, great. So again, so if you can come to the lectures, that'd be awesome. But if for some reason you can't, if you work or you have some other problem, you can always look at the videos. This time I'm going to try to upload the videos ASAP as soon as possible. So maybe after I eat something, then I'm going to upload them. So, but yeah, so you can do that. And if you still have any questions after looking at the videos, so please ask me anytime. Okay. So you also have my email address. That's right. So there are various ways that you can contact me. So feel free to do it. I mean, anyway, in any way you find it convenient. Okay. Any questions about the mechanics of the course?
Really surprised that you agreed to meet with us basically every day of the week at 4 a.m. So thank you.
Oh,
for
no
you.
problem. It's my pleasure. So don't mention it. It's my pleasure. So I like it. I love it. Yeah. So, but yeah, so you see, probably I'm going to have 1 week in which I'm going to teach you on site at 12 p.m. in Estonia, hopefully. Okay. All right. So let's start. So as usual, I'm going to use open board. Share screen first and then open board. Okay. And again, if you feel like you don't want to take notes, if you feel more comfortable just following my lectures and looking at the videos and looking at the whiteboard later on, that's fine. Okay, so if you want to make your own notes, that's also perfect. So let's start. So let me find my pen. Okay. Okay, so this is the first topic. Our first topic is preliminaries. Topic 1. And as I told you, the reason for including this section is to basically speak in the same language, mathematical language I'm talking about. And this is not because you have limitations in your language. You're very good in mathematics. The problem is that sometimes concepts are called in different way, even within the United States, okay, or in the UK. So that's the reason. And the first thing we're going to talk about is supremum and infimum. As supremum, sorry. And to start to cover this topic, I'm just going to remember briefly what the real numbers are. As you know from probably from your first semesters at Tallinn University, the real numbers is not only a set, is a set with two operations and one order relation. So this set and this order these operations and this order relation satisfy various properties. And these properties are usually called axioms. So we have axioms for addition. So which are those axioms? So they are, I'm not going to mention them in detail. So you have associativity. You have commutativity. You have the existence of an identity. And this identity is actually 0. And you also have the existence of inverses, which we call additive inverses, right? We also have properties for the multiplication. And these properties are, again, associativity, commutativity, the existence of an identity. This identity is actually 1. And we have the existence of inverses for numbers which are not equal to 0. And again, I think that you are taking algebra, abstract algebra. You see these properties, for instance, tell you that the real numbers with the sum is a group, is a commutative group. It doesn't matter, okay? So we're not talking about algebra. Then we have some properties which are called distributivity. Okay, there is only one. Sorry, there is only one property of distributivity. And then we have the properties for the order relation. So I'm not going to mention these properties. They are like 4 properties. But in addition to all of these axioms, there is one more axiom satisfied by the real numbers. And that's what we call the axiom of suprema. Which is also called the least upper bound property. Least. And I'm going to remember these properties. So one of the ways to express this property is saying that for every subset of R, which is non-empty, if S is bounded from above, then S has a supremum which lives in R. So again, I make emphasis on this. So the real numbers is a set with 2 binary operations and an order relation that satisfy all of these properties. These properties for the sum, the multiplication, this partial order, and this axiom is also satisfied. Okay, now my question to you is, you covered this axiom, right? You remember this axiom?
Yes.
Okay, great. So it's important. Well, I'm going to say it in the next page. On the next page, can I change the page?
Yes.
Yes. Okay. So with these axioms, these ones, these ones, this one, and these ones, you can define the rational numbers. But with this axiom, you have many other consequences, and I'm going to mention those consequences on the next page. So these are remarks. Okay, with the supremum axiom, we can do various things. We can construct the irrational numbers. So for instance, you can prove that square root of 2 is a real number. We can prove also that the natural numbers is unbounded. We can also prove the Archimedean property of R. So the Archimedean property basically tells you that for every epsilon greater than 0, there exists a natural number with the property that 1 over n is less than epsilon. You can prove also that for every real number, you can find consecutive integers such that that real number is between these two consecutive integers. And you can do more stuff. For instance, you can construct the Riemann integral using the supremum axiom. Okay. So all of these are consequences of the supremum axiom. And as you can see, the theory becomes richer, becomes more interesting with the supremum axiom. Without it, we couldn't have the irrational numbers, we couldn't have this property, we couldn't have this Archimedean property, and so on. Okay. So it's quite an interesting property satisfied by the real numbers. Okay. Since this semester I'm going to use the supremum axiom very often, what I'm going to do now is I'm going to prove some properties about the suprema. Just to remember some of the arguments used to prove those results. Okay. I'm going to prove a small lemma. I think this lemma is also in your textbook. Okay, this lemma tells you, suppose that S is a subset of the real numbers, which is non-empty. And suppose that A is a real number. Then you have that A is the supremum of S if and only if the following two properties are satisfied. A is an upper bound of S. And the second is that for every epsilon greater than 0, there exists some x in S with the property that A minus epsilon is less than x. And again, I'm going to do this because as you know, I don't teach theoretical courses at Tallinn University. I have been assigned mainly applied mathematics courses, and I'd like to make sure that we use the same arguments. Okay. So this is an if and only if. So we need to prove both implications. So suppose first of all that A is the supremum of S. And we have to prove this property and this other property. Now, since A is the supremum of S, remember supremum is the least upper bound of S. So that implies in particular that A is an upper bound of S. So this property is satisfied easily, right? we only need to prove the second property. So you start taking some epsilon greater than 0. So let epsilon be greater than 0. And we consider the number a minus epsilon. So a minus epsilon is less than a. And a is the least upper bound. So this implies that a minus epsilon is not an upper bound of S. Okay, maybe not an upper bound. And since it's not an upper bound of S, what we do is we negate the definition of being an upper bound. Not an upper bound means that there exists some X in S with the property that this X is greater than a minus epsilon. Did you follow me in this reasoning?
Yes.
Okay, great. Thank you. Hilary, right?
Yep, that's right.
Okay, thank you. Okay. So then you proved I into I. So now we are going to do the converse. And can we change the page?
We are ready. I don't know about other girls.
Yes.
How you do?
You can.
Yeah.
Okay, thank you. Thank you very much. So now we are going to do the converse. So we are going to suppose that these two properties are satisfied. And we have to prove that A is a suprema of S. So in other words, it's the least upper bound of S. Okay. Let's change the page. So, well, by hypothesis, A is upper bound of S. We have to prove that it's the least upper bound. Okay. So to prove that A is the least upper bound, and we are going to do that by contradiction. So suppose that there is an upper bound which is less than A. So suppose that B less than A is upper bound for S. Okay, so what I'm going to do is I'm going to use the second property, the property 2I. To that end, I'm going to define the following number. So we let epsilon be equal to A minus B. And you notice that this number is greater than 0. Well, then you can use the hypothesis. So the hypothesis 2I. So there is an X with this property. So by hypothesis, there exists some X in S with the property that A minus epsilon is less than X. And then you start to do calculations going to the left, a minus epsilon. What you can do is you can substitute epsilon. And you simplify. And what do you have now? Well, you have that b is less than x according to this inequality. But you suppose that b is an upper bound for s. Oops. Since it's an upper bound for s and x is in s, then this must be satisfied. And this is a contradiction. And the contradiction, we obtain the contradiction because we suppose that b is less than a. So in other words, it must happen that a is less than b for every b which is upper bound of s. So in summary, we saw that a is an upper bound. And for every other upper bound, a must be less than or equal to that number. And that's how you prove that a is the supremum of s. Okay. Any questions on the proof?
After the suppose b is less than a is upper bound for s, and the next word, is it like define? Or?
Yeah, define. Yeah, define. Yeah, define epsilon as this number.
Okay, thanks.
Okay. Oh, thank you. Any other questions?
No.
No. Okay. And I guess you could follow me like easily, right?
Yes.
Okay, great. So I'm going to talk briefly about limsup and liminf. They're going to be important in our studies. So we have the following definition. So suppose that xn is in this set, which for convenience, probably you saw this notation. This is the collection of all sequences. I'm sorry. All sequences in R. So suppose that you have a sequence. Okay, first definition. So here we say that xn converges to some x in R. So this is just the definition of convergence. So this happens if for every epsilon greater than 0, there is a natural number such that for every natural number greater than that one, this distance is less than epsilon. So please tell me, is this your definition of convergence?
Yeah, I think we had something very similar.
Okay. So, and it makes sense. So when do you say that xn converges to some number? If you can make the values of the sequence sufficiently close by taking the indexes sufficiently high, right? So this is the definition of convergence. So convergence to some number x. I'm also going to remember the definition of convergence to infinity or divergence towards infinity. Can we change the page? Yeah.
Yeah, we can move on.
Okay, thank you. So we say that xn goes to infinity if for every m greater than 0, there exists a natural number n such that for any n greater than or equal to n, xn is greater than or equal to m. So that's a definition of a sequence going toward infinity. And I'm also going to remember the definition of convergence to negative infinity. So this happens if for every m, there exists an n such that if this happens, then xn is less than or equal to minus m. Another standard definition. So let xn again be a sequence of real numbers. And suppose that x is a real number or plus minus infinity. Then we say that x, I'm sorry, x is a limit point of the sequence xn if there exists a subsequence of this sequence with the property that the subsequence converges to x. Okay, as I said before, this is also something standard, probably you also remember it. So this is the definition of limit point for a sequence. And you can remember also some of the properties. One of the properties is the following one. That if some sequence converges, then x is the only limit point of the sequence. Okay, so and remember, I would like to define limsup and liminf, and that's what I'm going to do next. So this is another definition. Suppose that xn is a sequence in the real numbers, and we consider the following sequences. One of them, the nth term is going to be the supremum of the xk for k greater than or equal to n. So this is a sequence of real numbers, and I'm going to consider the following, the other sequence, the infimum of xk for k greater than or equal to n. Is this clear that these two things are sequences of real numbers?
Yes.
Okay, thank you. Well, notice that this is a parenthesis, so you consider the supremum of xk for k greater than or equal to n. This sequence is non-increasing. Non-increasing. So as n gets bigger, you take the supremum over less terms. So that's why this is non-increasing. And I'm going to represent this in this way. So it doesn't increase. It doesn't mean that necessarily decreases, right? But it's non-increasing. On the other hand, this sequence, the infima of xk for k greater than or equal to n, is non-decreasing. Which means that these sequences are monotone. So you see, you have two sequences which are monotone, and you know that every monotone sequence converges, I mean, in the real numbers or the plus minus infinity. So in that sense, it makes sense to define the following numbers. So we define the limsup of xn as the limit when n goes to infinity of the supremum of xk for k greater than or equal to n. And as I said before, this exists in the extended real numbers. And in similar fashion, I'm going to define liminf. So it'll be the limit when n goes to infinity of this infima. Okay. Please let me know when to turn the page, ladies.
For me, it's okay.
Okay. So I'm gonna change it now. So we also define the liminf of xn as the limit when n goes to infinity of the infima of xk for k greater than or equal to n. And again, this number exists in the extended real numbers. Okay. A small remark, this is something also that you proved at some point. These are properties of limsup and liminf. So the limit superior, limsup of xn. This is by definition, we saw before in the previous page, this is the limit when n goes to infinity of the supremum of xk for k greater than or equal to n. So that's our definition. But you can see that this is also the infimum of over all n's of this suprema. And in similar way, you can also show that the liminf of xn is the supremum of the infimum. These are consequences of the fact that these sequences, this one and this one, are monotone. And we have an interesting result, which I'm calling it a lemma, that says the following: let xn be a sequence in R. Then it turns out that the liminf of xn is less than or equal to limsup of xn. Okay, so how about the proof? Well, there are various ways to prove it. I'm going to show you one way. First, notice that for every n in the naturals, the infimum of these numbers is less than or equal to the supremum of the same numbers. I guess we can say that this is obvious, right? And in the second step, I'm going to notice that this happens when the n's are different. So for any n1 and n2 in the natural numbers, it turns out that this infimum for k greater than or equal to n1 is less than or equal to this supremum for k greater than or equal to n2. Now, in the first step, we saw that this is true in the case when these numbers are the same. Right, so that's what this tells us. But now we're proving that this is true for any n1 and n2. And the way to prove this is simple, just take two cases. So case 1 is the case, let's say, when n1 is less than or equal to n2. Okay, so n1 is less than or equal to n2. You calculate the infimum of xk and calculate the infimum of xk now with less sub-indexes. And you compare them. Okay. Since here, look, we're supposing that n1 is less than n2. So here we have less sub-indexes than here. And that's why this inequality is satisfied. And we saw before, using the first step, this is less than or equal to the supremum of xk, where k greater than or equal to n2. This left-hand side is less than or equal to this right-hand side. That's exactly what we wanted, right? So it's simple. You would have to take the second case, but it's similar, and I'm going to mention that on the next page. Please let me know if we can change the page.
I think we can change the page.
Thank you. Okay, so case 2 is similar. So this is the case when n1 is greater than n2. And I'm going to skip the proof. Okay, so how do we reach the conclusion? So that'll be the third step. So I'm going to go back. We have these inequalities, which I'm going to call star. This is satisfied for every n1 and n2. On the right-hand side, I'm sorry, on the left-hand side, I'm going to take supremum, and on the right-hand side, I'm going to take infimum. I can do that because this inequality is satisfied for every n1 and n2. So take supremum on the left of star and take infimum on the right of star. And that's the way you see that liminf is less than or equal to limsup. Okay. So that's the proof. I don't know if you have any questions.
I don't have any questions right
Okay.
now.
Okay, and you are being able to follow me in the arguments?
Yeah.
Okay, great. I'm happy about that. So I'm just going to state a theorem without proof. This is important. So suppose that xn is a sequence in R. Then we saw that liminf and limsup exist. And moreover, they have an important property. They are limit points of xn. So for any sequence, these two numbers are limit points of xn. And moreover, if x is a limit point of xn, then it turns out that liminf less than or equal to x less than or equal to limsup. So in other words, liminf is the smallest limit point of a sequence, and limsup is the largest limit point of a sequence. So any other limit point is between the two of them. And an easy consequence is the following one. So let xn be a sequence in R. Then the sequence converges if and only if limsup is equal to liminf.
What does the coro mean? Or
What does what? I'm sorry.
I don't know. I read it as coro or I see.
Converges. I'm sorry. This is converges.
No, the red word before that.
Corollary. Sorry. Okay. Yeah, so this coro is for corollary. Okay, so those are properties that we are going to use later on. I'm going to talk briefly about convexity. Some of the most important or most powerful theorems on optimization require this condition. So my definition is the following. Suppose that S is some subset of Rn. Then we say that S is convex if the following is satisfied for every x and y in S, and for every lambda between 0 and 1, lambda times x plus 1 minus lambda times y is in S. Now that's a definition, but this definition has a geometric meaning. So, can we change page?
One moment, please.
Okay, yes, of course. Yeah.
Okay, we can change the page.
Okay, thank you. So what's the meaning of convexity? You have a set. This is my set S in Rn. You say that S is convex if for any 2 points inside S, so this is X and this is Y, the straight line joining these 2 points is always within the set. Okay. And that's because any point here can be described as a point of the form lambda x plus 1 minus lambda y, with lambda between 0 and 1. So this is the meaning of convexity. So a set is convex if for any 2 points inside the set, the straight line joining them is within the set. And there are various examples of convex sets. One of them is this one. So you consider this set, which I'm calling D. The set of points such that its norm is less than 1. This set is convex. And you can prove it easily. So probably you did it already. So you saw that any ball, open ball, is actually convex. There are various properties satisfied by convex sets. One is the following. So suppose that you have a family of convex sets. Suppose that all of these are convex. Then it turns out that the intersection of all of them is also convex. So intersections of open sets, I'm sorry, intersections of convex sets are convex. And for the proof is pretty straightforward. So you let X and Y be in the intersection and lambda be between 0 and 1. Okay, so you use properties of the definition of intersection, then that means that for every alpha, X and Y is in S alpha. And you remember that lambda is between 0 and 1. And here is where you use convexity. So since S alpha is convex, then for every alpha in lambda, in omega, sorry, you have that lambda X plus 1 minus lambda Y is in S alpha. And this happens for every alpha, so.
Sorry, we have a question about this sign, alpha, where alpha is like this big sign for every alpha that belongs to where?
Omega is a set of
Okay.
indexes.
Okay.
Yeah, thank you. Yeah, sorry, so yeah, I'm assuming that this is just a set of indexes. Okay. Then you have that this vector is in all of these S alphas. And it follows that it's in the intersection of all of them. And by definition, this tells you that the intersection is actually convex. And I'm going to give you a result for you to prove this is also fun. So this is a lemma also. Suppose that you have S and T, which are convex. Then you define the sum of both sets as this set. It turns out that then the set is also convex. The proof, I'm going to leave it for you, leave it to you to prove. Okay, so this is also very simple, relatively simple. These are just some properties of convex sets. I guess that you already studied convexity, right?
Yes, we did.
Great. So just do this proof at your convenience. Let me just save. Oh, save. It said save. Export.
Natuke salvestab.
Can you go back after?
Yeah. Yes, I'm just saving. There you are. Is there any question, ladies?
I don't have any questions.
Do you have any questions?
No.
Yeah.
No
Me
questions.
and Deb are still taking notes, so no questions yet.
Okay, so you're taking notes. Okay, so if at some point you have any question, please let me know. What we're going to cover in this course will be basically it'll be based on vector calculus and a little bit of metric spaces, but that's it. So the material should be straightforward, and but if you have any questions, please let me know. Up to this point, how do you feel?
Okay, I think it's doable.
Okay, okay. So just please check the material that we covered. And again, if there are questions, just let me know. If at some point I'm going too fast, also let me know. Or if I'm going too slow, also tell me. Okay, so I don't want you to fall asleep. Okay. Have you finished taking notes, ladies?
Yes.
Yes. Oh, okay. So, thank you for being here, and I'll see you tomorrow and the day after tomorrow. So, any comment?
Not really.
No.
Not really. And from the other ladies?
No. No.
No questions. Okay. So this time I also have ladies in this course. Okay, so like last semester. Okay. Okay. So let me stop recording.